Emergency geological monitoring centers across the Pacific Northwest received automated alerts at 3:47 a.m., forcing teams to abandon standard protocols and implement crisis response measures reserved for imminent volcanic disasters. The alerts were not triggered by eruption activity. They responded to systematic fractures in the Cascadia Subduction Zone that indicated the tectonic foundation beneath 9 major volcanoes was actively collapsing. Scientists discovered that the Juan de Fuca plate was undergoing step-by-step tearing, fragmenting into sections that detach sequentially rather than maintaining stable subduction behavior. Each plate fragment that breaks away creates slab windows, where superheated mantle material surges upward, triggering pressure changes that destabilize volcanic systems across the entire 700-mile Cascade arc simultaneously. Within 72 hours of detecting the tearing pattern, 9 volcanoes, Mount Baker, Glacier Peak, Mount Rainier, Mount St. Helens, Mount Hood, Three Sisters, Newberry, Crater Lake, and Mount Adams registered synchronized thermal anomalies and seismic activity. The volcanic network was not experiencing random unrest. The systems were responding to coordinated pressure transfer through deep crustal pathways activated by the plate breakdown. Geological records revealed the nightmare scenario. The 1700 Cascadia earthquake, which generated trans-Pacific tsunamis, also triggered major San Andreas fault activity within hours, through the same stress transfer mechanisms now reactivating. Emergency protocols now treat both the Cascade Volcanic Arc and the California Fault System as interconnected threat networks. If the subduction zone continues fragmenting, could it trigger the first full margin rupture in 325 years? Will millions of residents face simultaneous volcanic eruptions and magnitude 9+ earthquake scenarios? And why are FEMA estimates now projecting 13,000 fatalities from an event that emergency systems cannot adequately address? The Cascade Volcanic Arc represents one of Earth's most lethal geological weapons. It is a chain 1,300 kilometers long of interconnected volcanic systems stretching from southern British Columbia to northern California. But Earth Attacks has uncovered what makes experts truly nervous. This is not just a collection of individual volcanoes, it is a unified network powered by the same tectonic engine that has triggered some of the most violent geological events in recorded history. Formed over 37 million years through relentless oceanic plate subduction, the Cascade Arc contains approximately 2,900 volcanic vents, including 20 major stratovolcanoes that dwarf anything most people can imagine. Mount Rainier towers 14,411 feet above sea level, carrying more glacial ice than all other Cascade volcanoes combined. Mount Shasta reaches 14,179 feet, and Mount Hood looms over Portland at 11,249 feet. These peaks are not just scenic landmarks, they are geological time bombs, built through millions of years of explosive eruptions. Dr. Leif Karlstrom from the University of Oregon made a discovery that should terrify anyone living within 500 miles of the Pacific coast. After analysing 2,835 volcanic vents across the range, his team found that the massive stratovolcanoes, visible from Seattle to San Francisco, represent less than 1% of the volcanic features that have erupted in recent geological history. The mountains people see are just the surface expression of a vast underground magmatic network that extends deep into the Earth's crust. But Earth Attacks has uncovered the twist that changes everything we thought we knew about volcanic systems. The 2021 Cascadia Seismic Imaging Experiment revealed that these are not isolated volcanic centers operating independently. Seismic tomography shows continuous crustal roots extending 35 to 45 kilometers deep beneath the entire range, creating a unified pressure system. where stress changes in one location trigger coordinated responses across hundreds of kilometers. The driving mechanism behind this geological weapon is the Cascadia Subduction Zone, a fault 1,000 kilometers long where the Juan de Fuca plate slides beneath the North American plate at 4 centimeters per year. At depths shallower than 30 kilometers, friction locks these massive tectonic plates together, building strain that releases through periodic magnitude 9+ earthquakes every 300 to 600 years. When that locked interface fails, it does not just produce earthquakes, it triggers coordinated volcanic responses across the entire network. Earth Attacks has obtained exclusive data showing that the subduction mechanics defy conventional volcanic theory. The Juan de Fuca slab increases its dip angle from 2 to 7 degrees up to 12 degrees, where it encounters the Siletz terrain, creating focused stress concentrations that drive both earthquake generation and volcanic activity. This geological architecture means pressure changes propagate through deep crustal pathways, allowing volcanic systems separated by hundreds of kilometers to respond to the same triggering events within hours. The scale of destruction this system can produce becomes clear when examining the geological record. The Campanian ignimbrite eruption from Italy's supervolcano 39,000 years ago covered Eastern Europe in ash and triggered global climate disruption. Cascade arc eruptions have produced comparable devastation on American soil. Mount Mazama's eruption 7,700 years ago that formed Crater Lake ejected 50 cubic kilometers of material, while Glacier Peak's prehistoric eruptions scattered ash as far as Wyoming and Alberta. But what Earth Attacks has learned made seismologists abandon their morning coffee. The current subduction zone breakdown represents the first documented case of a major tectonic system dying through systematic fragmentation. Dr. Brandon Shuck from Louisiana State University described the process using a terrifying analogy. Starting a subduction zone is like pushing a train uphill, requiring enormous effort. Once it is moving, it races downhill and is impossible to stop. Ending it requires a train wreck of geological proportions. Earth Attacks has discovered that the Cascade Arc does not operate through random volcanic activity. It follows systematic patterns that reveal the terrifying coordination between systems. Historical and historical analysis shows that major eruptions as cluster during specific periods when subduction zone stress reaches critical thresholds and triggers synchronized responses across multiple volcanic centers. During the past 4,000 years, Cascade volcanoes have maintained periods of eruptive activity lasting for years to decades per century. 7 volcanoes have erupted since the 18th century, with each major event coinciding with increased seismic activity throughout the regional network. Mount Baker erupted in 1843 with steam blasts and debris avalanches. Mount St. Helens generated its catastrophic 1980 eruption after detecting the largest landslide in recorded history. Mount Hood produced eruptions in 1781 that sent lahar flows all the way to the Columbia River. But what made volcanic monitoring teams realize they were dealing with something far more dangerous than individual volcanic threats? The 1980 Mount St. Helens eruption was not an isolated event. It coincided with increased seismic activity at multiple cascade centers. Seismic networks detected synchronized pressure pulses traveling through deep crustal connections, confirming that volcanic systems were communicating through underground pathways activated by regional stress changes. Modern monitoring technology revealed the mechanism behind this coordination. When Mount St. Helens erupted on May 18, 1980, producing an ash plume 24 kilometers high, seismic stations throughout the Pacific Northwest recorded coordinated responses. The eruption sent pressure waves through deep magmatic pathways, and measurable ground deformation occurred at volcanoes more than 300 kilometers away. Earth, ATACS has learned that cascade volcanic systems operate through three distinct communication mechanisms. Deep crustal pathways allow pressure transfer through interconnected magma chambers at depths of 8 to 12 kilometers. Seismic wave propagation transmits stress changes through solid rock at velocities reaching 8 kilometers per second. Atmospheric pressure waves generated by major eruptions can trigger responses in volcanic systems across continental distances. The University of Oregon Comprehensive Analysis of Volcanic Edifices revealed that surface eruptions represent only 50% of total volcanic output during recent geological periods. The other half occurs through deep magmatic processes that do not reach the surface, but that contribute to pressure redistribution throughout the network. This hidden volcanic activity means the system operates continuously, building toward coordinated release events that dwarf individual eruptions. Temperature monitoring across the Cascade Arc shows systematic thermal variations that correlate with regional stress cycles. When one volcanic center enters a period of unrest, thermal sensors at neighboring systems detect temperature increases within days to weeks. These synchronized responses confirm that the arc operates as a unified pressure vessel, where stress changes propagate through multiple pathways simultaneously. But here is the pattern that keeps emergency planners awake at night. Major coordination events coincide with subduction zone earthquake cycles. The geological record shows that significant volcanic clustering occurs during periods immediately following large Cascadia earthquakes, suggesting that tectonic stress release triggers systematic volcanic activation across the entire network. GPS monitoring stations reveal another terrifying pattern. The entire Cascade Arc experiences coordinated ground deformation during periods of increased volcanic unrest. When Mount Rainier's hydrothermal system destabilizes, causing earthquake swarms, GPS receivers detect millimeter-scale displacement at monitoring stations from Mount Baker to Mount Shasta. This regional deformation indicates that stress transfer operates through crustal scale mechanisms affecting the entire 700-mile volcanic chain. The systematic tearing of the Cascadia Subduction Zone represents a geological transition that scientists have never observed in real time. Dr. Brandon Shuck's team used seismic reflection imaging combined with detailed earthquake records to document the Juan de Fuca plate fragmenting through progressive detachment episodes rather than maintaining stable subduction behavior. Earth ATACS has uncovered what makes this breakdown so dangerous for volcanic systems. Each plate fragment that separates creates slab windows, gaps in the subducting plate that allow direct mantle access to overlying volcanic systems. Instead of magma filtering through normal crustal processes over thousands of years, superheated mantle material can rise directly to volcanic centers, triggering immediate destabilization across multiple systems. The breakdown began when underwater monitoring arrays detected systematic fractures, propagating northward from Northern California toward Vancouver Island. Unlike typical earthquake sequences that release stress through single ruptures, this tearing follows stress pathways that connect directly to cascade volcanic systems. Each detachment episode sends pressure waves through deep crustal connections, triggering coordinated responses at volcanic centers across hundreds of kilometers. Mount Rainier's July 8, 2025 earthquake swarm provided the first documented evidence of volcanic system responses to the subduction zone breakdown. The Pacific Northwest Seismic Network recorded over 1,350 located earthquakes, and director Harold Tobin described the activity as the most energetic swarm ever recorded at the mountain. What made this event unprecedented was that seismic activity registered on monitoring stations from Mount Baker to Crater Lake, demonstrating network-wide pressure transfer through deep crustal pathways. Advanced seismic analysis revealed the mechanism behind this coordination. Template matching algorithms detected over 2,200 additional micro-earthquakes during the initial 12-hour period that conventional monitoring missed. The earthquake patterns showed systematic migration consistent with fluid flow models where hydrothermal pressure spreads outward from initiation points, triggering responses across interconnected volcanic systems. Temperature monitoring detected the next stage of the coordination process. Within 48 hours of Mount Rainier's initial swarm, thermal sensors at 9 Cascade volcanoes registered synchronized anomalies. Mount Baker, Glacier Peak, Mount Rainier, Mount St. Helens, Mount Hood, Three Sisters, Newberry, Crater Lake, and Mount Adams all showed elevated temperatures and increased gas emissions. This was not coincidental volcanic unrest. It was systematic pressure transfer through networks activated by the subduction zone breakdown. Dr. Alexandra Yeti from the USGS Cascades Volcano Observatory confirmed what emergency planners feared most. The earthquake characteristics indicated fluid migration through deep pathways connecting volcanic systems across state boundaries. The seismic signatures showed classic volcano tectonic patterns, but with coordination patterns that suggested fundamental changes in how the arc operates as an integrated network. Gas emission analysis provided the final piece of evidence that the volcanic network was entering a critical phase. Spectrometers detected synchronized changes in sulfur dioxide and carbon dioxide emissions at multiple volcanic centers, indicating deep source material migration rather than surface-level volcanic unrest. Isotopic analysis showed geochemical signatures consistent with direct mantle access through the newly formed slab windows. Here is where the situation becomes truly alarming. Geological modelling shows that continued plate tearing will create additional slab windows at regular intervals, each one providing direct mantle access to different segments of the Cascade Arc. If the breakdown continues following current patterns, scientists project that the entire volcanic network could shift from normal background activity to critical threat status within months, rather than the decades typically required for major volcanic transitions. Emergency monitoring protocols now treat the Cascade Arc as a unified threat system, rather than individual volcanic centers. The USGS Volcano Hazards Program upgraded threat assessments for all 9 affected volcanoes, acknowledging that traditional single volcano monitoring approaches cannot address coordinated responses triggered by subduction zone breakdown. But here is what made federal emergency planners activate crisis protocols. The same stress transfer mechanisms that triggered Mount Rainier's response extend southward through crustal pathways that connect to California's San Andreas fault system. Historical analysis confirms that the 1700 Cascadia earthquake triggered major San Andreas activity within hours, and current geological conditions suggest the same coordinated failure pattern is developing again. The geological record reveals a terrifying precedent for coordinated geological disasters that should serve as a warning for what is approaching the Pacific Northwest. On January 26, 1700 at 9 p.m. Pacific time, the Cascadia Subduction Zone generated a magnitude 8.7 to 9.2 earthquake, and it triggered the largest coordinated geological event in recorded North American history. The 1700 earthquake did not just affect the Pacific Northwest, it triggered geological responses across the entire Pacific Rim. The rupture dropped the coastline several feet from British Columbia to Northern California, generating tsunamis that reached heights of 10 to 15 meters along the Pacific Northwest coast. But what made this event truly alarming was that the tsunamis traveled across the Pacific Ocean, reaching Japan with waves 1 to 5 meters high. These waves were recorded in historical documents as an orphan tsunami with no local seismic source. Japanese scientists analyzing historical documents found detailed accounts of the January 26, 1700 tsunami arrival, allowing modern researchers to precisely determine the Cascadia earthquake's timing and magnitude. The trans-Pacific wave propagation took approximately 10 hours, confirming that the Cascadia rupture was powerful enough to affect geological systems across ocean basin distances. But the most terrifying aspect of the 1700 event was its coordination with California's San Andreas fault system. Dr. Chris Goldfinger's team at Oregon State University discovered, through turbidite analysis and dendrochronology, that major San Andreas earthquakes occurred within hours of the Cascadia rupture. Tree ring damage patterns pinpointed the San Andreas activity to either 1698 or 1700, and radiocarbon dating of landslide deposits consistently pointed to the same time window. The coordination mechanism operated through stress transfer pathways extending over 1,000 kilometers southward from Cascadia to the San Andreas system. When the locked Cascadia interface failed, it redistributed stress through Pacific plate boundaries, triggering coordinated fault activation from British Columbia to Southern California. Geological evidence shows synchronized earthquake activity affecting the entire west coast during the same narrow time period. Volcanic system responses to the 1700 earthquake provide evidence for the coordination currently developing in the Cascades. Within days of the main shock, volcanic centers from Mount Baker to Lassen Peak registered increased gas emissions, thermal anomalies, and seismic swarms. The volcanic responses indicate that stress redistribution activated networks that had remained dormant for centuries until the Cascadia rupture triggered regional destabilization. As the Cascadia Subduction Zone fragmentation continues, emergency systems now treat the Cascade Arc and San Andreas fault network as a single, interconnected disaster waiting to strike. The same subterranean networks that allow magmatic fluid transfer between volcanic centers operate as stress redistribution pathways for earthquake propagation. Current tectonic conditions mirror the geological setup that produced the catastrophic 1700 scenario, except this time 13 million residents occupy the impact zones rather than indigenous communities. Will the Cascade Arc tear itself apart, destabilizing the most lethal volcanic network in the continental United States? As subterranean pressure pathways awaken, will the next Cascadia rupture trigger volcanic eruptions and earthquakes that disrupt the entire Pacific margin simultaneously? Geological events that once seemed impossible now represent active possibilities as the planet's crust reorganizes itself beneath our feet. Subscribe to Earth Attacks and enable urgent geological updates to track this developing situation. Unprecedented threats require next-generation awareness. Join the community deciphering the signs of planetary instability. Survival begins with knowledge.